Okay, last time we have been discussing about the restricted three body problem, and then we started to find out about the Lagrange point, or the what we call as the librational points, where in the synodic reference frame with respect to two primary bodies, one primary body and another secondary body, which are quite heavy with respect to a tertiary body, but which is very small, infinite, or say infinitesimally small. So, at the librational point, this tertiary body, it appears to be at rest in the synodic reference frame. Okay. So, we continue with the same discussion in this lecture. Okay. So, we started with the equations. Okay. So, these are the three equations that we started with. So, here for our convenience, we wrote R 1 s is equal to R 1 and R 2 s equivalently as R 2, okay, and omega s can be replaced as omega. So, the integration of these three equations with respect to t, it produced the Jacobi's integral. Okay. So, that we wrote as integration of above three equations produced Jacobi's integral, which we wrote as x dot square plus y dot square plus z dot square is equal to x square plus y square plus 2 1 minus mu star and the left hand side here, this is nothing but v square. So, the same thing we wrote as v square x square y and plus 2 1 minus mu star by r 1 plus by r 2 minus c, and this can be written as 2 u minus c is equal to 5 minus c, where u is equal to 1 by 2 times x square plus y square plus 1 minus mu star by r 1 plus mu star by r 2. Okay. So, here the phi which is appearing, so phi we wrote as a function of x y z, and for v equal to 0, okay, phi which is a function of x y and z. So, this describes the equation of a surface. So, we will keep discussing about these things. expand it further. So, what we were discussing about the librational points and the or the equilibrium points, which are also called the Lagrange points. So, librational points or the Lagrange points, they arise once we set x double dot y double dot and z double dot equal to 0 and x dot y dot z dot equal to 0 and substitute into these equations, and resulting equations they provide us the librational points. So, we need to solve them. So, also I stated that the librational point, it is nothing but the double points. So, double points they can be defined as, if a curve is given. So, this curve may intersect itself in a point. So, at that point we can have two tangents. So, if this curve is defined by f x y. So, dou f x dou f by dou x equal to 0 and dou f by dou y equal to 0, this gives the double points. Okay. So, if we do the same operation on this equation, okay. So, we have the Jacobi's integral available. So, we differentiate the Jacobi's integral or the function phi is equal to c is available to us. So, we can work with this and we can prove this. So, phi equal to c. So, here we can write it as this v square is equal to phi minus c. Okay. So, with this equation it is possible to work out using this partial differential and find out the librational points, or either you directly use the equation which we have developed earlier and set into this the x double dot y double dot x dot y dot and z double dot equal to 0. Of course, here z dot is not present in this equation, but this the equilibrium point also refers to the x dot y dot equal to. So, we have the x double dot y double dot z double dot equal to 0 and x dot y dot z dot equal to 0. This gives us the equilibrium points, or the what we call as the librational points or the Lagrange points or Lagrange points. So, rather than working with this differentiation, this partial differential, we start working with this and set into this equation these constants. Okay. So, the solution to this will be, so last time we have worked out all those things and we saw that the resulting equations were minus omega square x r 1 cube x minus r b 1 minus mu 2 by r 2 cube x plus r b 2, and this is our equation number 4. This is our equation number 5, and then 0 equal to minus mu 1 z by r 1 cube minus mu 2 z by r 2 cube. Okay, this is equation number 6. So, now this three equations, equation number 4, 5 and 6, they can be solved to find out the values of x, y and z. So, from equation number 6, from this equation, this is very easy to solve. We can see that this equation can be written as mu 1 by r 1 plus mu 2 by r 2 times z equal to 0 from equation 6. Okay. Now, the quantity which is present here, this is non-zero, okay. And therefore, this implies that z equal to 0. So, this is the solution that we get for z equal to 0. So, this simply implies that the point, this implies that the librational points lie in the orbital plane of the primary and secondary bodies. Okay. Now, we can proceed to solve the equations 4 and 5. Now, equations 4 and 5, 5 and 6, 5 and 6 can be solved to yield x and y. So, solving the equation 5 and 6 we can do in the normalized form, and also we can do in the non normalized form. So, both are possible. So, on the normalized scale what we have seen that we set mu 1 is equal to g m 1 and g we set as 1. So, therefore, this got reduced to m 1, and similarly we have mu 2 is equal to g m 2 is equal to m 2. Okay. Moreover, we wrote m 1 as m 1 plus m 2, this is equal to 1, and then we defined m 1 as 1 minus mu star and m 2 is equal to mu star. So, we have this equation number, sorry, this is equation number 4 and 5, this is not 5 and 6. So, we have equation number 4 and equation number 5, which is related to the x and y coordinates. Okay. So, from equation number 5, we have minus y equal to mu 1 is nothing but m 1 is equal to 1 minus mu star, and mu 2 similarly is this quantity here. So, we can simply write this as 1 minus mu star. You can have a look of this equation again. Okay, so, we are replacing in this quantity mu 1 is nothing but 1 minus mu star. Okay, similarly, mu 2 is mu star. So, this will be replaced by 1 minus mu star divided by r 1 cube y minus mu star r 2 cube times y. Okay, and we can rearrange them. So, 1 minus mu star by r 1 cube plus by r 2 cube and assuming y not equal to 0 in this equation. So, this leads to, this implies 1 minus mu star by r 1 cube plus mu star by r 2 cube, this is equal to 1. Okay. Now, from equation 4, minus x is equal to minus 1 minus mu star y by r 1 cube x minus mu star. Here this quantity is nothing but x b 1, this we have explained in earlier lecture. So, mu star by r 2 cube times x plus 1 minus mu star. Okay. So, the solution that we got here, this we can write as equation number 7. Let us say this is equation number 8. So, substituting equation 8 into equation 7 into equation 8, okay. So, first we will sort out the common terms. So, this we can write as minus sign, we can cancel on both sides. So, let us remove the minus sign at this stage itself. So, 1 minus mu star r 1 cube x, and from here we sort it out, this is mu star by r 2 cube times x, and then from this place we will have plus mu star r 2 whole cube times 1 minus mu star minus mu star times 1 minus mu star divided by r 1 whole cube. So, if we substitute from equation 7 this quantity into this. So, this becomes x is equal to x plus mu star r 2 whole cube 1 minus mu star this is r 1 r 2 whole cube and this is r 1 whole cube. Okay. So, these two cancel out, leaving us with r 1 cube is equal to r 2 cube. So, this simply implies r 1 is equal to r 2. So, this is our result number 9. And we have already taken the distance x a b, okay, that is the distance between these two particles a and b as 1, okay. And if this is the point b, so from here we measured this distance as, this mass was 1 minus mu star and this distance we measured as, wrote as mu star, okay, and this distance we wrote as 1 minus mu star and this mass as mu star, okay. So, this is m 2. So, this we are replacing with mu star and m 1 we are replacing with 1 minus mu star, okay. So, already our distance r 1 2 or x a b we can write as r 1 2. So, r 1 2 equal to 1, okay. This we have already written. So, if we have the from equation number 7, this is our equation number 7. Now, in this equation if we substitute R 1 is equal to R 2. Okay, so, this will yield us 1 minus mu star times mu star is equal to R 1 cube is equal to R 2 cube. So, this cancels out and this implies R 1 is equal to R 2 is equal to 1, and therefore, this quantity is nothing but equal to R 1 2. Okay. So, it shows that the equilibrium points they lie in a equilateral triangle. So, here the points we have the point number 1 which is indicated by A, the point number 2 which is indicated by B. So, this is M 1 and M 2, okay. And the mass M. So, this distance was our R 1 and this distance was R 2 and this is R 1 2. Okay. So, this one is equal to this one and this one, and on a normalized scale they are equal to 1. So, therefore, these 3 points they lie in the equilateral triangle. So, from here it is obvious that one point will lie here, another point will appear here downwards somewhere here in this place. So, if we have the earth here in this place and this is our moon. So, for the earth moon system, one point will appear here, another point will appear here in this point, and they will appear always at the same distance, because here because it is equilibrium point. So, this mass is going to appear from these two places to be always present in the same point. So, as the moon is moving and the earth is also moving. So, they have their barycenter somewhere lying. Suppose this is the heaviest mass, the earth is here. So, suppose barycenter is lying here in this place somewhere, this is our point B. Okay. So, earth will be moving along around this point and the moon will also be moving around this point. So, this is our earth and this is our moon. Okay. So, about this point they are moving like this, and while the M is remaining at a constant distance from this point and this point. So, it will always appear in the same point, and later on we will discuss more about this graphically how the whole thing looks like. So, beside these 2 points, so this we can name as the L 4 and the L 5. So, L 5 will appear downward somewhere in this place. Okay. So, this solution will later on we will see, we will find out using the by solving these equations 4, 5 and 6, we will find out the values of x and y from this place, and obviously, z also. So, and these are going to give us the points L 4 and L 5. So, these are our librational points or Lagrange points. Okay. Okay, so, alternately we work in terms of equation 4, 5 and 6. So, this is going to produce a more general result, and from there we will further develop and look into graphically what does it mean to have the librational points, and how according to the variation in V. So, either I can have the 0 velocity which is the bounding surface beyond which the particle cannot go, or if we have V which is positive, okay, which is always positive. So, if we have certain positive value of the V, so how the particles will be moving, the third particle will be moving with respect to this primary and the secondary bodies M 1 and M 2. So, from equation 6 we can write this is our equation number 6. So, from here it is apparent z equal to 0. So, from equation 6 we have mu 1 plus r 1 plus mu 2 by r 2 times z equal to 0. So, simply this implies z equal to 0, because quantity in bracket non-zero. Okay. So, here we term this as equation number 9. So, this is our equation number 9. Now, from equation number 5, we get omega square, this is equal to mu 1 by r 1 cube plus mu 2 by r 2 cube. Assuming y this is not equal to 0. So, this is our equation number 10. Okay. And equation number 4 gives us, so from equation 4, omega square x, this will be equal to mu 1 by r 1 cube mu 2 by r 2 cube x plus r b 2. So, this is equation number 11. Now, from equation 10, so we put the equation 10 equation 10 into equation 11. So, what we can do? So, before this we need to little rearrange this. So, rearrange. So, already we have done the rearrangement earlier. Okay. So, this we can write as mu 1 by r 1 cube plus mu 2 by r 2 cube x plus mu 2 by r 2 cube r b 2 minus mu 1 by r 1 cube r b 1. So, this quantity we can substitute from equation number 10. So, this quantity is nothing but omega square x. So, omega square x and omega square x, this cancels out, as earlier we have done in the normalized form, but here in this format we are going to get little more insight. So, this is mu 2 minus mu 1 this is so they cancel out, and this implies mu 2 by r 2 cube times r b 2 r b, and this we term as our equation number 12. Moreover, equation 10 can be written as mu by r 1 2 whole cube, because omega square is equal to nothing but mu by r 1 2 whole cube, where r 1 2 is the distance between the points A and B, okay. And mu is nothing but, here mu is nothing but g times m 1 plus m 2. So, this is equal to mu 1 by r 1 cube plus mu 2 by r 2 cube. Also we know that r b 1 plus r b 2, this is equal to r 1 2. So, total distance between the point 1 and 2, and moreover m 1 times r b 1 equal to m 2 times r b 2. So, these two results can be utilized along with the equation that we have just now written, equation number 12, to derive useful results. So, from this we can write as 12, this is 13, this we can term as 14, and this is 15. So, from equation 15 we have m 1 by m 2 is equal to r b 2 by r b 1, and m 1 by m 2 if we multiply up and down by g. So, this will nothing but equal to mu 1 by mu 2. So, this is our equation number 16. Okay. Also we will have mu 1 plus mu 2 is equal to mu. Okay. This is we write as equation number 17. Now, it is a inserting into the equation number equation number 13. So, inserting these results into equation 13. Okay, so, we will have mu by r 1 2 whole cube, this is equal to mu 1 by r 1 cube plus mu 1 by, now mu 2 by r 2 cube we need to replace. Okay, so, mu 2 by r 2 cube we can replace from equation number 12, mu 2 by r 2 cube it can be replaced from equation 12. So, mu 2 by r 2 cube, this becomes mu 1 by r 1 cube times r b 1 by r b 2. So, we can take it out, mu 1 by r 1 cube. So, this gives us r b 1 r b 2. So, this implies mu 1 by r 1 cube, and this we can sum it up. So, r b 1 plus r b 2, this is nothing but equal to r 1 2. So, we can write this as r 1 2 divided by r b 2 is equal to mu by r 1 2 whole cube. Now, similarly, mu 2 by r 2 cube so we will do little more expansion, we will write it little more properly. So, we will write this as mu 1 by r 1 cube is equal to mu by times r 1 2 is equal to r 1 2 whole cube times r b 2. Similarly, we can write okay, this is the result that we got earlier, mu 2 by r 2 cube. This is the result that we had in the equation number 12. So, we utilize this result. Okay. So, this quantity will be equal to now mu times r b 2. So, we have here this equation we can utilize. Let us name this also as equation number 19. So, from here we will have so, we can take out from mu 1 by r 1 cube from here and insert into this equation here in this place. So, this is our inserting into this equation. Similarly, we can write this is by putting from equation 19. So, mu 1 and mu 1 by r 1 cube we are replacing here. So, this comes in terms of this quantities here mu times r b 2 divided by r 2 to the power 4 times r b 1 by r b 2. So, this cancels out and what we get is or r 1 2 times mu 2 by r 1 2 r 2 whole cube, this is equal to mu by r 1 2 whole cube r b 1. Now, all these equations can be utilized. So, this is our equation number 20. To find out the relevant relationship between these quantities, so we can look into equation number 19 and 20. Okay. So, from equations 90 and 20, R12 whole cube R12 by R1, so this R12 by R1 whole cube times mu 1, this is equal to mu RB2 this is one equation. Another we get R12 to the power 4 from equation number 20 to the power R2 cube time is equal to mu by mu 2 times RB1. Okay. So, these are the two equations after rewriting we are getting. So, from here the useful results can be derived. So, if we expand them further, so this can be written as mu 1 plus mu 2 divided by mu 1 times R B 2. So, this is nothing but 1 plus mu 2 by mu 1 times R B 2, okay. And here this will yield us mu 1 plus mu 2 divided by mu 2 times R B 1. So, this will be 1 plus mu 1 by mu 2 times R B 1. Okay, now, both the equations they are available here. So, these equations, let us say this is our 21 and this is 22. Okay. So, R B 2 can be expressed in terms of R B 1. Okay. So, we can express R B 2 in terms of R B 1, which we have written earlier. So, R B 2 is nothing but mu 1 by mu 2 times R B 1. So, use this result to resolve the things further. So, this becomes the equation 21 will become equation 20 will lead to R 1 2 to the power 4 R 1 cube. This becomes 1 plus mu 2 by mu 1 times mu 1 by mu 2 times R B 1. So, here we can cancel out mu 1. Okay, if we multiply inside, so this becomes 1 plus mu 1 by mu 2 times R B 1. Okay. So, this we name as equation number 23. Now, we can compare equation number 23 and this equation number 22. So, we have in equation number 22 R 1 2 to the power 4 by R 2 whole cube equal to on the right hand side 1 plus mu 1 by mu 2 times R B 1. In this equation on the right hand side also we have 1 plus mu 1 by mu 2 times R B 1, while the left side differs. So, by equating these two equations 22 and 23, equating equations 22 and 23, this will give us R 1 2 to the power 4 by R 2 whole cube equal to R 1 2 to the power 4 by R 1 whole cube. Okay. And this implies 1 by R 1 is equal to 1 by R 2, and this implies R 1 is equal to R 2. Also from equation 21, R 1 to the power 4 divided by R 1 cube, this is equal to mu by mu 1 times R B 1 is equal to this we have written as 1 plus okay, and mu 2 by mu 1, this quantity we can replace as R B 2 by R B 1 multiplied by R B 1. So, this leads up to R B 1 plus R B 2 is equal to R 1 2. So, this implies R 1 to the power 4 by R 1 whole cube is equal to R 1 2, and this implies R 1 is equal to R 1 2. Therefore, from this result, this is result number, we can write this as 24 and this we can write as 25. So, from 24 and 25 we get R 1 is equal to R 2 is equal to R 1 2. Okay, this is what the result we established on the normalized scale. So, there it was very easy, while here it took some time to work it out. Okay. So, this implies the 3 points or the 3 masses lie on an equilateral triangle. So, this is 17. Okay, now we have once worked out all these things. So, next we can look into the what will be the values of x and y. Okay. So, we need to work it out. Working for values of x and y. So, we know that x minus R B 1 square plus y square, this is the quantity R 1 2 square, and similarly we have x plus R B 2 this is our equation number 26, this is 27. So, utilizing the previous results, and here we have already we see that the right hand side in both the cases they are referring to the same quantities, okay, because this distance we wrote as R 1 square and this distance we wrote as R 2 square. So, this quantity was, because we have already proved that R 1 equal to R 2 is equal to R 1 2. So, from 26 and equation 26 and 27 we can write x minus r b 1 x plus r b 2 square plus y square. Okay. So, this implies x minus r b 1 is equal to plus minus x plus r b 2. Okay. Next, we utilize some of the results, like we can prove it r b 1 plus r b 2, this we have already written as equal to r 1 2. So, from here it can be written as r b 2. Okay. So, r b 1 is equal to r 1 2 minus r b 2, and r b 2 again can be written as mu 1 by mu 2 times r b 1, okay. And therefore, r b 1 earlier also we have proved this result. So, r 1 times r b 1 times 1 plus mu 1 by mu 2, this becomes r 1 2, and this implies r b 1 is equal to r 1 2 mu divided by mu 1 plus mu 2. Now, from equation 28, taking negative sign, we can write this as or x is equal to 1 by 2 r b 1 minus r b 2. So, r b 1 r b 2 we have right now expressed. So, we can use those expression to resolve it further. So, in sorting for r b 1 and r b 2, this is r 1 2 mu divided by mu 1 plus, okay, here we have this equation mu 1 plus mu 2 r b 1, this is mu 2 here, so missing. So, this is mu 2 minus r b 2, we have written as mu 1 by mu 2 times r b 1. Okay. So, we can simplify it first and then we can write it again 1 by 2 r b 1 minus r b 2, we can write as mu 1 by mu 2 times r b 1. So, this becomes 1 by 2 mu 2 minus mu 1 by mu 2 times r b 1. So, what we get x as 1 by 2 times r b 1 times 1 minus mu 1 by mu 2. In r b 1 we have already written in terms of r 1 2. So, this becomes r 1 2 times mu 2 by mu 1 plus mu 2, and then multiplied by mu 2 minus mu 1 by mu 2. So, they cancel out and ultimately we get mu 2 minus mu 1 by mu 2 plus mu 1. So, this is the value of x that we get and multiplied by of course R 1 2. Okay, so, this is our equation number this is 30. Okay, now we can work out for y. Okay, so, we can work along the same line. Okay, x we can substitute from here. So, this will be R 1 2 by 2 times mu 2 minus mu 1 by mu 2 plus mu 1. Now, R b 1 can be written in terms of R 1 2. So, after that simplification, we can write this as 1 by 2 mu 2 minus mu 1 mu 2 plus mu 1 R b 1 by R 1 2 mu 1 by mu 2. Okay. And further simplification of this can be done. So, we will continue next time. So, we will see that y can be written as plus minus under root 3 by 2 times R 1 2. So, we can see that the x and y both have been written in terms of R 1 2, which is the distance between the points A and B. Okay. So, these two useful results, and z we have already written that seen that z equal to 0. Okay. So, using this we will be able to find out where the point is exactly located. So, we continue with these things next time, and beside this, these are the 2 points. Beside this we have 3 points, other points which are collinear. Okay, that is they lie in the same on the same line. So, those 3 points how to work them out, that we will see next time. Okay, thank you very much.